your lab write-up. First off, you need a title. Title's always centered and underlined. So you can go ahead and title it Conservation of Mass Lab. And then you write the word purpose, kind of like a resume style, bold, underlined, and colon. And the purpose always has two parts. What we did, and once you get data or whatever we did, we analyze it. So and that's what we're trying to teach you. So in this lab, what we're going to do is actually mix baking soda and vinegar and measure the mass before and after to test the conservation of mass law. So you can abbreviate that and make it a little bit shorter or make it your own words. What we're learning is we're practicing good scientific technique. So what we're going to do, the first lab will have inherent sources of error, things that lead to bad data, you could say. And then you get to redesign the experiment, repeat the experiment with your own design, and see if you get better data. So what we're doing, we're testing the conservation of mass using vinegar and baking soda. And what we're learning is we're going to repeat the experiment to improve the design. That's the core of this experiment. The background. We always have definitions. This one has quite a long background, but typically it won't be this long. But go ahead and look up conservation of mass. Reactants, I'll go ahead and tell you. It's what you mix together in a reaction. Products are what are made. Open system is it's self-defined. It's an experiment that's open, so the reactants and products can escape during the reaction. A closed system is just that. We're going to close the system so the reactants or products can't escape. And then we're going to have you understand the equations and several different terminologies. So all this next section are saying the same thing. Reactants, products. We can say it in common terms, we can say it in chemistry terms, and we can say it in chemistry symbols. So reactants today in common terms are baking soda plus vinegar. And when you say an arrow in science, that's a fancy way of saying yields, or a symbol to say yields. So baking soda plus vinegar yields a liquid plus gas plus salt. In chemistry terms, baking soda is called sodium bicarbonate, and we're going to be using it throughout the whole semester, so this is one we want you to memorize. So instead of saying baking soda in science classroom, we sound fancy. We say sodium bicarbonate plus, no, not vinegar. Chemistry terms, we say acetic acid. See how much more intelligent you sound? Sodium bicarbonate plus acetic acid yields, and it turns out it actually makes water, carbon dioxide, these are the bubbles, and sodium acetate. And chemistry symbols, NaHCO3 plus CH3COOH. This is baking soda, sodium, and this second part is the bicarbonate. Vinegar, acetic acid, what makes it acid is this hydrogen right here. And this part is called acetate, the CH3COO. Plus water is H2O, most people know that. Plus CO2, most people know that. Plus sodium acetate. So there's the sodium clicked together to the acetate. Conservation of mass data and calculations. And so we've set this up for success for you, but in the future, we're going to want you to be able to do something similar. In fact, in part 2 of this lab, you'll be making your own, so keep this as a guide for your future use, like block day. So, first thing we need to do is get the mass of just our reactants. So, mass of baking soda. In order to do that, we're going to mass an Erlenmeyer flask, and I have another YouTube video showing you the background of the lab and safety. So you're going to mass it empty. Then you're going to put some baking soda in. We'll give you the baking soda. And so if you subtract those two, actually the mass of B minus A, you'll get just the baking soda. Same thing applies with the vinegar. You'll mass the empty beaker, put vinegar in, subtract the two, and you'll get the mass of just the vinegar. So remember, we can't keep re-emphasizing this enough. Our reactants is the baking soda, fancy way of saying it, sodium bicarbonate, and vinegar, fancy way of saying it, acetic acid. Not the beaker, that's not involved in the reaction. The flask is not involved in the reaction. And so the mass of reactants, we're just going to add up how much baking soda and vinegar we have. And that adds that up. And then you get to slowly mix the two. And again, I want to emphasize this point. As soon as you mix sodium bicarbonate and baking soda, those reactants disappear, and shazam, you're making new products. You're making bubbles, carbon dioxide. You're actually making water, H2O. And then the white powder that remains, instead of it being the baking soda, that's the sodium acetate. And so after the reaction is all done, you're going to mass the Erlenmeyer flask with the products, not the reactants. Okay? And then we're going to subtract out the flask from way back here. You measure the mass of the flask. And so you'll subtract that out and you'll get the mass of the products. So the big thing we're interested in is mass of reactants. Does it equal the mass of the products? The conservation of mass law says it should. So we're going to see if it does. Reactants, the mass of the products. We analyze the data, and typically that means some real simple math. So check this out. Mass of reactants, mass of products. If you find the difference, you found the mass lost. So hopefully you didn't gain mass. If you gain mass, we've solved the world's energy crisis. But if you are really careful with your measurements, the mass of the reactant should be greater than the mass of products. Now we're going to ask some questions down below here of why you think that may be. Okay? Now, calculate the percent mass lost. So we're going to compare how much was lost to how much we originally had. So the equation for that is mass lost divided by mass of reactants. So this number right here in step C divided by this number right here in step A. And then the reason we multiply it by 100 is to make it a percent. We always want you to show your work and box in the final answer. So in this class, we don't want you to write just a bunch of numbers. We want you to label them. Okay, so it's even in a perfect world you write the equation, like the words, M-A-S-S-L-O-S-T, write the equation. Next, the substitution. So in here you put the number of mass lost with grams, mass of reactants in grams times 100. And then the third step is boxing the final answer with, the label. In this case, it's percent. What evidence was there of a chemical reaction? So while you were watching this reaction, what did you see? Did it change colors? Bubbles, that's a good evidence one, obvious. Does that white powder look the same before compared to afterwards? Anything that was evidence that something funny was going on in there. Which product was lost, and explain why? Hint, hint, hint. Let me back up here. It was, in our definitions, an open system. And if you look at our products, we have liquid, gas, and salt. So because it was an open system, what do you think escaped? Nemo. Bubbles! My bubbles. Hint, hint, hint. Okay, I'll give you the answer. So, and then, did you prove the law of conservation of mass wrong in this lab? Explain. In other words, because the mass of the reactants did not equal the products, did we break this law and have to write a bunch of new books? Or is there something wrong with the experiment? And if you think something's wrong with the experiment, please explain.